Yeah, welcome to this lesson. And in this lesson, we'll be treating real gases and ideal gases. So, real gases and ideal gases. Let's head into the lesson. So, first, I'll start by an introduction. This topic tries to explore the differences between real gases and ideal gases. So, while real gases are given by the formula PV equals nRT, as we know, this actually provides a useful model that we could use to determine the definition or the behavior of real gases. So ideal gases have the formula PV equals to nRT, which is the general gas law, while real gases, they kind of have a similar formula or a formula that was coined off from this ideal gas formula. So real gases deviate from this behavior, the behavior of ideal gases, under certain conditions. So understanding the reasons for this deviation is crucial for accurately describing gas behavior in practical situation. So we'll be seeing how and why these real gases they deviate from ideal behavior. So let's go. An ideal gas is a hypothetical gas that perfectly follows the assumptions of the kinetic molecular theory. So previously we talked about the kinetic molecular theory, and these assumptions from the kinetic molecular theory include the negligible volume. They say gases have negligible volume, and also they have no intermolecular force of attraction. And they also say that gases are they have perfectly elastic collision. So in our previous lesson, in the last lesson or some lessons behind this, we talked about how or what perfectly elastic collision means. So it means a condition where when a particular molecule or gas molecule strikes the body of its container, it does not lose its energy. So this kind of collision is called a perfectly elastic collision. So there is the assumption from kinetic molecular theory that states that all gases they have a negligible volume. That's their volume. The volume of each molecule of gas is negligible. It also states that no intermolecular force of attraction exists. That there's no interaction between one molecule and another molecule of gas. And also, it also asserts that it also tries to predict that, to assume, not really predict, to assume that um, the collisions are perfectly elastic. So while these theories are reasonable in some extent, some other extent they tend to be flawed. So when we are trying to look at real gases, it's these real gases that tend to alter this theory from being really a law. So we'll see how these actually come into play. So let's head in. Real gases deviate from ideal behavior at two different conditions. So at high pressure and low temperature. So under these conditions, gas particles are closer together and the intermolecular forces of attraction become significant. So these are the conditions where real gases tend to behave like ideal gases. Or at high pressure, when the pressure is high, we remember from Boyle's law, when pressure is high, the volume becomes low. So when the volume becomes low, we can then be able to see the volume of gas, which kinetic theory said that it is supposed to be negligible. So, but when we reduce the volume, that is the space where these gases can move about, you will then find out that truly these gas they have a particular volume and it cannot be negligible when pressure is high. So, under low temperature, we can also see that the intermolecular force of attraction become significant because when the temperature is low, these gases tend to be attracted to one another. There's a kind of molecular attraction. That's what happens when we see stuff like liquefied gases. Liquefied gases, when temperatures are low, we will find out that these gases will tend to behave like as though they are liquid because of the intermolecular force of attraction that would come into play at these low temperatures. So the finite volume of particles cannot be ignored at high pressure, and also the intermolecular force of attraction cannot be negligible at what they call it at low temperature. So these factors are what cause real gases to deviate from the normal ideal behavior. So let's see. So now, in order to account for the deviation of real gases from ideal gases, there was a formula that was coined out, and this formula is called the Van der Waals equation. And this equation was introduced by scientist Van der Waals, and in trying to accommodate for these behaviors under high pressure and low temperature, he introduced um, two parameters in the formula, in the normal formula, the normal real gas formula, and these parameters include A, which represents letter A, which represents or which tries to account for the intermolecular force of attraction, and also included another parameter B, which tries to account for the finite volume of gases. So the equation tries to provide a more accurate description of gas behavior, especially under these non-ideal conditions. So this is the van der Waals equation, and the van der Waals equation is given as this: P plus, and so normally in the normal ideal gas equation we just had P V equals to nRT, but now to account for the deviation we see stuff like P, then they brought in this parameter n squared A all over V squared to account for the changes under high pressure, and also minus NB to account for the changes under low temperature. So A represents the attractive force between molecules, and B represents the residual volume of molecules. So from this, by this introduction of parameters, by this parameter introduction, we are able to account for the volume that comes into play at low temperature, and also for the attraction that comes in, the volume that comes into play at high pressure, and the attraction that comes into play at low temperature. So with those parameters, try to explain the behaviors or try to account for the deviation from ideality of gases. So for example, gases like ammonia and water tend to deviate significantly from ideal behavior due to strong hydrogen bonding. So in contrast with noble gases such as helium rather, and neon, with minimal intermolecular forces. So more closely approximates, or more close, which in contrast with these noble gases such as helium and neon, with minimal intermolecular forces of attraction. So more closely approximate ideal gas under a wide range of conditions. So experimental data supports the idea that no gas is truly ideal. So from normal experiments, we've been able to prove scientifically that in real sense, no gas is completely an ideal gas. Ideal gas is just an hypothetical gas that's not really real. They don't really exist. So at every temperature, at low temperature, at room temperature, and atmospheric pressure, many gases behave like real gases. Many gases behave like ideal gases at room temperature and atmospheric pressure. But when the conditions begin to change, they begin to deviate from this behavior of ideal gases. And I think that's the reason why there is then the model from van der Waals that tries to account for these deviations. So in conclusion, the understanding of this behavior of real gases is important in many scientific and industrial applications, including chemical engineering, respiratory therapy, and also environmental science. So accurate gas models are essential for predicting the outcomes and the designing of equipment. So this knowledge, as I said at the beginning of this lesson, is very crucial that we understand them, because they will be able to help us predict the way different gases would behave, and industrially it can be used for designing industrial plants and also equipment that will be used. So that will be all for this lesson, and I'll be saying goodbye.